Hello students, welcome back to another lecture on Turing Machine. Here we are going to learn examples on Turing Machine. The very first example that we are going to look here is for the language A raised to n, B raised to n. Do you remember we had constructed a PDA for this? This language has the strings made up of A's followed by B's, and number of A's and B should be same. If you remember, we had used a stack to check whether the string is of the required type. We had a strategy where we pushed all A's into the stack, and for every B we read, we popped one A. If the string has equal number of A's and B's and A's followed by B's, then when we finish reading the string, we have only the bottom symbol, that is Z0, left out into the stack and nothing else. So this is how we had constructed a PDA. But today, here we are going to design a Turing machine. So let's see how we can design a Turing machine for a context-free language. Here we have a machine. You can see the initial state here, Q0. The halt with acceptance is actually the state Q4, which is double circle, acts as an accepting state. Let us assume a sample string double A, double B. So let's check how the string gets accepted. So assume the string is A, B, B, and then you have a blank. As we discussed in the previous lecture, you know that the tape head will be always placed by default at the first symbol. So where are we now? We are in the initial state Q0. What is the machine reading? It is reading A. Now, what is the strategy? Let me explain. We will convert this first A into X. We'll keep on reading these A's until and unless we come across the first B. And we will convert this B into a corresponding Y. Again, we will move back to the recent X. Keep it as it is, move towards right, and again we find another A. We will replace this A with X. We will again move across towards right direction till we come across the next first B. As soon as we find the next first B, we will be converting this into Y. So did you get the strategy? For every A we converted into X, the corresponding B is converted into Y. We will again move back towards the recent X. So here we are. We will keep it as it is and move towards the right. So we are at which place? This place. Do we have any more A's? No, we don't. Now we have to last confirm that there are no additional B's at this place. So how do we do it? We just keep on reading these Y's, and the immediate what we find is a blank immediate next to the last Y. This configuration means we have exactly equal number of A's followed by B's. So it's a very simple strategy. For every A you converted into X, we have another B converted into Y. So keep on moving or doing this. So how is it performed? Initially we are here in Q0. We read the first A, convert it into X, and move the tape head towards right. Whatever the A's in between we have, we just keep on reading them and moving ahead, that is in the right direction, till we come across the first B. This first B will be then converted into Y, and we again move towards left. While moving towards left, we may read those A's and Y's in between and keep on moving towards left until we come across the most recent X. Keep it as it is and move towards right. If we find another A, the same thing is repeated. Again, this A is replaced into X. Move again towards right till you find the next first B. Replace it with Y, and again keep on moving towards left till you come back towards the recent X. So keep on repeating this cycle of converting A's into X and B's into Y's. And finally, when you keep that X as it is and move towards right and find that there are no more A's, but directly a Y on the right of X, what will you do? Keep on reading those Y's, keep on moving towards right till you find that there is an immediate blank on the extreme right end of your Y's. And the minute this configuration is met, you will land into the accepting state, or what you call it as halt with acceptance. I think you have got this, the working of this Turing machine for the language A raised to n, B raised to n. Students, what do we observe here? We have designed a machine for A raised to n, B raised to n, which is a context-free language. But just imagine if the language is A raised to n, B raised to n, C raised to n. Then what will happen? We cannot design a PDA for this. We have already discussed. Rather, we can prove using pumping lemma that A raised to n, B raised to n, C raised to n is not a context-free language. Now, here is the difficulty. If you cannot design a PDA, what next? But yes, we can design a Turing machine for the language A raised to n, B raised to n, C raised to n. So it's possible that we can confirm we have equal number of A's, B's, and C's. So even though this is a context sensitive language, yes, we can design a Turing machine for this language. And this infinite tape with the tape heads movement both towards left, right, adds to the power of this Turing machine. And hence, Turing machines are more powerful than your PDAs. So you can see here the recent example that we were talking about. You can see the two A's were converted into X and the two B's were converted into Y. And finally, we have accepted this string double A, double B. So this machine is a general machine which can accept any string of the type A raised to n, B raised to n. Okay, so I would again revise the definition of Turing machine. What you will find in your textbooks is it is defined as a mathematical model of a machine with 5 tuples: Q, sigma, tau, delta, and Q0. But some authors also define it to be with 7 tuples. But it doesn't make any difference. It's as good as same. Q, the set of states. Sigma, you all know, it's the set of input alphabets on which we design the language. Tau is a tape alphabet. Delta is a transition function that we learned recently. Q0, the unique initial state. Yes, this symbol, which can be of any different style also, which acts as a blank symbol. And F stands for the final state, which we learned is also called as halt with acceptance. Now, we can have deterministic Turing machines. What we have seen here, we can have non-deterministic Turing machines, as well as we can have some output producing Turing machines also. So now, if you look at and if we summarize, what we learned is deterministic Turing machine, which has a tape in which the both ends are infinite. The tape has input, and when I say you have output producing DFAs, you can create or produce the output, and the same output can be written onto the concept. Very soon we will be learning in the lecture what are the variants of Turing machine. In the variants, we will be learning non-deterministic Turing machine, multi-tape Turing machine, universal Turing machine, and doubly infinite tape Turing machine. Students, remember, in these 2 lectures, we have only covered the basics of Turing machine and Turing machine as a language acceptor. As I said, there are some more things to learn. I just now said that the Turing machines can act as computers. They can process, they can produce some output for the input that they are reading. So they are called as computable Turing machines. So the next lecture that we are going to learn is on computable Turing machines. Thank you, my dear students.